today will just be review, just like class yesterday. But of course, today we're going to review the calculus things that could be on the test. So to make sure we're clear, the first thing, the calculus things that couldn't be on the test would only be the calculus that we've covered with motion. Not all of the stuff that was like in the first calculus review, right? We're only talking about the stuff we've used in physics class, not in reviewing math. So the first type of problem you could have is starting with, actually, I said starting with acceleration. I should have put this on the next page because the next one is, no, third one, I don't know. I have here starting with acceleration, derive the kinematic equations, or you could do it in the reverse, which is what we have here, starting with an equation for position, find velocity and acceleration. So let's do this problem. This is a problem from one of the practice things that I have on Moodle. And so it gave this equation, x is equal to 3.00 t squared plus 5 minus 10.2 over t. And it says to find the speed, well, it says to find the acceleration at 2.45 seconds. But in order to find the acceleration, I need to first find the speed. So my process in getting to here is going to be first to take the first derivative. Now, we've all taken derivatives for some time. We had the practice. So I'm trusting everyone can find these derivatives. You know, the more physicsy thing is knowing that that's what you have to do. And so if you're on the test, you know, if this came up, you'd say, well, to find the acceleration, I'll need to take the second derivative and then plug in the time. That would be your concept part. So, right, as somebody said in class yesterday, so where do you write in the concept? In class, I say it. If you look at my practice, you know, my solutions for previous exams, you'll see it written there so you can see, you know, I try to put the concept first when I'm doing the actual writing. So taking the derivative, 2 times 3 is 6. Derivative of the constant is 0. And then derivative 10.2 over t is going to be, change it from a minus to a plus, 10.2 over t squared, right? It's changing the sign because I brought down a minus 1, then lowered the power from t to the minus 1 to t to the minus 2, hence over t squared. And so then my acceleration is taking the derivative once again, 6.00 minus, bring down the minus 2 is why I have a minus sign, 20.4 over t cubed. And then finally, we just had to find the acceleration at this time. So we put in our number. Don't forget to put divided by or you get a completely different answer. What do you get, Aaron?
4.613.
That's the total answer?
Yeah.
Okay.
But that's not the answer.
And of course, that would only be good to 3 significant digits, so I'll take off the last one there. And since I didn't have units with my numbers, I didn't really put the units in, but it should be meters per second squared if it's an acceleration. And so if I gathered what you were saying beforehand, before I blurted in, they probably had 1.61 is what you were saying?
Yeah.
Well, this is correct.
Okay.
And this is what you said you did.
Yeah.
Okay, so there's an example. Now, this was not going the same direction, but that's okay because I'm just going to go to the next slide, which says, starting with a jerk, derive the kinematic equations. Yes, sir.
Just a quick question. Can we do unit analysis through a derivative?
Can you do unit analysis through a derivative? I'm not exactly sure what you mean by that question. Can you clarify?
If we're given units for the original position equation,
yes.
What happens to those as we take derivative?
Okay, so what happens to the unit? Now I understand. What happens to the units through the derivative? Well, this is where treating a derivative like an actual fraction explains the answer immediately. If you're doing dx dt, the units of x are position, the units of t are time. So dx dt, since d just means an infinitesimal change in it, still has the unit of x. So that should have units of meters per second. Well, how do you see that in your derivative? Well, when you do the derivative, you are effectively dividing everything by this value, right? So if you look at this, I had t squared, it became t. Now, I'm not just dividing, I have the other things that came around. But in terms of units, I have divided by t, so the units were seconds squared for this part, and now they're just seconds for that part. And likewise, go over to this last one, it had units of 1 over second, now it becomes 1 over second squared. And then, of course, we have the numbers had to have the other units to make the correct units. So this here, of course, this had to have, the 3 had to have units of meters per second squared, and the 5 had to have units of meters, and the 10.2 had to have units of meters times seconds, which I would usually write as seconds times meters so you don't get confused with milliseconds, right? It doesn't make a difference technically, it's just so I don't get confused. And then if you follow through, each one will have the right units. Do you have a question, Jonathan? Or
Not really. Sorry, I just have an input.
It's just, yeah.
I was just like,
It's all good. Okay, any other questions? Okay, so let's go to this one. Let's suppose we have a constant jerk. Now, the kinematic equations that the other class knows are the kinematic equations for, well, it is a constant jerk, but it's a jerk of 0. That is for a constant acceleration. So this is just going one step further and saying, let's say the acceleration is changing at a constant rate. And so if that's the case, given this relationship, the first, J is constant is what I'm saying in this case. What were the other things you said, Cody? Like the derivative jerk? Snap, crackle, and pop. Yeah. I've never heard that, but it's excellent. It certainly sounds like something physicists would come up with. So if you have a constant jerk and you want to integrate this up to find, well, what's the first thing you find if you're going to integrate up from the jerk? The acceleration. So what's the process you go through to go up? What's the first step you have to do? You start with this equation and separation of variables. So the first thing you have to do is separate variables. So I'm going to take this and multiply both sides by dt. Right, whatever. Multiply everything by dt so that I end up with j dt is equal to dA. J is a constant, so I only have 2 variables, t and a. I have both of them in numerator positions with their d's here. It's all separated. The left side of the equation only depends on time, the right side only on acceleration. So we have 2 independent equations that have to be equal, which means if I integrate both sides, they're still going to have to be equal. So that's what our next step is. We separate variables and then we integrate. So I integrate this from t initial equals 0 to t final. This from a initial to a final. Notice I have a initial and a final because, well, it's not a constant acceleration. You integrate these and it's a pretty simple integral since it's constants on both sides. And so I'd have j times t final minus 0 is equal to a final minus a initial. Now, why did I have t final and a final in my limits? I did it for a technicality. What's that technicality? Your limit can't be the same as the variable that you're integrating. It's a technicality. Once I'm done, I'm going to be happy to now relax this and take away my finals and say at any time t, the acceleration at that time, because final just meant at whatever time I stop. So it's purely a technical reason why I do that. I just don't want mathematicians to get angry with me. How is this integral here different than if I had done integrals without limits? I would have a plus c instead of that, well, in this case, minus a initial. And on the other side, we'd have a plus c, but you'd have the two c's and just combine them into a new c. Right? Plus c1 equals blah, plus c2. Just combine them over and say c is equal to c2 minus c1, or however you want to do it. So our constants, these are the things that would have been the constants, well, j times 0, and the a1 if we had done them without limits. But we're doing them with limits because we're finding for a situation where you start with specific parameters, not just a random situation. So now solving this for acceleration. That's the equation I've just found. I just rearranged it to solve for acceleration. Now the next step, I have the acceleration. I want to keep moving toward position. So what's the next step in the move toward position? Integrate. What's my equation I'm going to integrate? Okay, there are a lot of answers, which is great. That means a lot of people are thinking, I can't accelerate what I have, or accelerate. Can't integrate what I have right now. I have to do something else first. So what is the one thing I have to do first?
Substitute dv dt.
I have to substitute acceleration as dv dt. Right? I don't have any d's here. I can't integrate without d's. So I now have to substitute dv dt is equal to a initial plus jt. Now, of course, I'm out of space on this. Let me add a blank page. This is the weirdest thing. I guess it wants me to put in pages that are the same size as what I'm using, but I don't want to. I want to put 8.5 by 11s, and it's like at the very bottom. Just in case you wonder why I do these things. All right, so now we have the equation dv dt is equal to a initial plus jt. It's really rinse and repeat. At this point, I have to go back to the same instruction I started with, separate variables, and then integrate. So separating variables, what are the two? You do have to identify the two variables. So I ask you, what are the two variables? It's very simple, just because that's part of the thinking process. What are my two variables? T and V. And so how do I separate variables here? Yeah, multiply both sides by dt. And so I have dv is equal to once again, independent equations are equal to each other, so I can independently integrate them. Notice I could have let time initial not be 0, but we just always say, start your problem at time equals 0. It's going to take away terms from the derivation. And so doing these integrals, I now am going to have v final minus v initial is equal to a initial just making sure we're clear. I do have to put in my limits there. Because I just have polynomials, when I put in a limit of 0, it's just going to disappear. But it's not like magically disappearing. It's disappearing with good reason. Solving this for v final then. And the last step I do is relax myself to get rid of the finals now that I'm out of my integral. And so there's my speed kinematic equation for constant jerk. And then, of course, the last thing I'm going to do is rinse and repeat a third time. So it's kind of silly for me to ask, so what do I do now? You've already done it twice. The third time, you better remember v is equal to dx dt. So separating variables, you all know, multiply both sides by dt. So I'll have dx is equal to integrate both sides one last time. And that gives me x final minus x initial equals v initial t final plus 1/2 a initial t final squared plus 1/6 j t final cubed. Drop my final, solve for x final. There's my answer. It wasn't technically hard, and I did the same thing 3 times, but just seeing it done, I think, is worth some time. Did you have a question?
Did you want us to put the limits for the? Or if it's
I did put in the limit. Did I not write for some? Yeah, I did the analysis with the limit. I got less and less verbose in my writing as I went along.
But for the exam, do you want us to still show that?
For the exam, now that you've done that calculus review where I want you to be very explicit, as long as you have enough there for me to know, yeah, she did the integral right, I'll be good. If you did it wrong, well, then you have a problem. But if you did it right, and you have enough there for me to see, yeah, she did it right, we'll be okay. Great.
Just kind of question general for the test. So I looked at, I saw some of your ones you put up there for us to look over. And some of the problems you've got like over a page worth of work. Because you were very specific as to what steps were taken. Do you need to be that explicit?
No, my answers, they take me a long time because I'm trying to be super explicit. If I was taking the test, I would not be writing nearly as much.
Okay.
Yeah.
So what kind of, the concept is part of the questions, obviously, which
Yes.
you explained. So are you looking for more of like a 2 or 3 sentence?
For the concept, yes. I'm only looking for a 2 or 3 sentence thing for the concept.
Okay.
And on this first test, it's really easy to do in 2 or 3 sentences usually. I've already done the solution for the test you're taking this afternoon. I still have some long descriptions there. But that's because I want students to be able to look at the solution and understand if they had a mistake, what I was doing and so on.
Okay.
So I have more verbose than I expect from you.
Okay.
We're not going to have to solve this equation for any variables, are we?
You mean like find the time when x is 3?
Because that's like almost impossible.
Yeah, the old quartic, we're not going to solve a quartic equation. You don't have to worry about it.
Okay, good. Just making sure.
You do have to solve, too late now. Coming out of my mouth. You do have to solve a quadratic. All right. So, any more questions before I move on? How many people have ever had to solve a quartic equation before?
I plugged it into a program on my calculator.
We didn't have programs on our calculators when I was in high school. So there are 2 people who had to do it like I did in high school. It was, it's special. Okay, moving. So what we've done so far is we've gone both directions. We've taken an equation for x and take derivatives down to find speed and acceleration. We've taken an equation, in this case, we took one further than what general physics did for the jerk and integrated up to find position. So those are two of the likely things you can actually, what you can have on the test has to be a variation on one of those two, pretty much. You know, it's going to be calculus. And so this here is a variation on what we've already done. We have an equation, x is a function of time, and it says find the speed and acceleration at any moment. Well, that's basically what we've done, right? So what was the first step? How do I find the speed? V is dx dt. Here's a shortcut we use in physics. If you put a dot over variable, that means you're taking a derivative with respect to time. Now, in calculus, you probably learned things like f prime. In physics, that is very specific. That's df dx. That's a position derivative if it has a prime. It's a time derivative if it has a dot. And of course, that better be f of x. If it was f of y, you wouldn't do df of x or df dx. So that's just a shortcut thing that you may see me use from time to time. Come on. I've been doing the homework on my Samsung tablet with a different piece of software, and my finger erases on that one. That's what I was trying to do. Okay, let's just stick with this. Derivative of a cosine omega t. A and omega are cosine are constants. How do you find the derivative of cosine? Okay, derivative of cosine minus sine times the derivative of the inside. You have to use the chain rule. So just like before, that we could say that x of u is equal to a cosine of u, where u is equal to omega t. And so dx dt is equal to dx du dt. Right, that's the chain rule. You had a homework problem that had you using it. So here, dx du is going to be minus a sine of u, and then multiply that by du dt. Well, u is omega t, so the derivative of that is just omega. So there's my speed as a function of time. And to find the acceleration, A is dv dt. What's the derivative of sine omega t?
Cosine.
Cosine. And then we have to bring out the omega from the chain rule. So not doing it a second time, notice it's cosine, not minus cosine. I should have more space in the screen. I just noticed now. Fixed it. So that's minus a omega times another omega, omega squared, cosine of omega t. One last thing to note. I could put a as a function of position here. It's a very easy substitution. How would I write a as a function of position? To answer that question, start with what is the equation for position?
X equals a cosine omega t.
A cosine omega t.
And you solve that for t.
And so, well, in this case, I'm going to do it a much simpler way. That would work, but that would be a lot of work. Whereas here, I noticed there's a, that's not the color I thought I'd chosen. There's the color, whoops, there's the color I thought I'd chosen. A cosine omega t. Those two things together are position. And so this is just minus omega squared times position. This is something that we will learn about when we get to rotational motion. But the calculus here, this is just the positional calculus that we've learned, so it could be on the test. Any questions about this? I like to ask of this specifically before I go to the next topic, just so people aren't still cogitating on it. Of course, committee meetings, I always have this problem. We talk about something, 5 minutes later, I raise my hand. Going back to that topic, I've been thinking, and very disruptive. Okay. Motion of a real object. When an object moves through a fluid, it experiences a viscous drag. What's an example of an object moving through a real fluid? The ball going through the air. A person falling from an airplane. Those are objects going through viscous fluids. A lot of people don't think about air as a fluid, but a fluid is just something that flows. Air certainly flows. It's a fluid. So when an object moves through a fluid, it experiences a viscous drag. For low speeds, the drag can be approximated as linearly proportional to the speed. Find the equation for speed and position as a function of time. Now, there is a force aspect to this. I have an object, and it's moving through viscous material, and let's assume that there's nothing pushing it. So it's something like I just fired a bullet out of a gun. Once it gets out of the barrel, there's no longer any gas pushing it down the barrel. And it just has the viscous force slowing it down. It does have gravity pulling down, and we're ignoring the vertical, just looking at the horizontal. So if we look at the horizontal, the forces that are acting on it, well, let's do a full free body diagram. If it's traveling with a velocity like this, what forces would be acting on the bullet? Air resistance, the one we're talking about. So I would have the force of air resistance. And real, what's the other force, the vertical one? Gravity. What about force normal? It's not touching anything, right? We're not going to have forces on the test. I want to be clear. The force aspect I'm talking about is not going to be on the test. But there could be the follow-up part that comes from that. So if we look at this, no. You do have what we call an upward buoyant force because the air pressure is a little bit higher at the bottom of the bullet than at the top, but that's really small. And if the bullet is not tumbling, then we're pretty much done.
Acceleration of the bullet due to gravity doesn't cause air resistance?
No. If it's moving downward, then we'd have air resistance, but the air resistance is going to be the opposite direction of its motion. Not in my picture, it's not. Give it a second, it will be. Right. Right. As soon as it starts falling down because of gravity, but right now we're horizontal. And we're going to only look at the horizontal aspects as we go on anyway. Okay. Force of gravity is mg. Force of air resistance, we have for our equation here that it's approximately linear with speed, so that's going to be equal to some constant times the speed. Now, if I use Newton's second law, sum of the forces in my x direction is equal to the mass of the bullet times the acceleration in the x direction. So looking at this picture, this force is in the negative x direction. So I would substitute minus BV for the sum of the forces in the x direction is equal to the mass of the bullet times acceleration in the x direction. Now we have an equation that we can actually work with because, and unfortunately I have to add another slide here. I'll get better at this. So minus BV. I'm going to drop the subscript B. It's the mass of the bullet. And I'll just drop the subscript X for acceleration in the X direction. So minus BV equals MA. Now we're into the kinematic. So this is where you could actually start the problem for what's going to be on the test. If I want to find, as the problem says, find the equation for speed and position as a function of time, there's no time here. Yeah. I'm not going to panic. I'm not going to panic. What am I going to do? Gila? Substitute for A. We will substitute that A is equal to dv dt. That has time in it. And so I will have minus bv is equal to m dv dt. Now we have a first order linear differential equation. That's the name for it. The first order linear differential equations are the only kinds that you can solve. Otherwise, you have to take differential equations to learn how to solve them. There's one of the things like of rank 1 or something like that. So what do we do at this point?
Separate the variables.
Separate the variables and integrate. Right? There's only really 2 tricks in our game: separate variables and integrate, or take derivative. So we're going to separate variables and integrate. What are the 2 variables? Well, just tell me. When I separate the variables and integrate, what equation am I going to have?
BV dt equals MdV.
Need to divide by v.
My bad. Wrong.
Right? It was a step in the right process, but it wasn't the final answer. Now I'm going to do one more thing because I like to. That's right. Somebody knows how I like to think about my problems. I want that dv by, the v term without any other stuff, because it's going to give me the natural log. So now I have the equation that says dv over v is equal to minus b over m dt. Integrate both sides. The left side becomes natural log of v, my limits. The right side becomes minus b over m. There I put the t initial in. That's as explicit as one could be. And this is the way I would normally write it, just, because I can do limits in my head. All of you can probably do limits in your head. You just I wanted you to show that you understand how to do it in the first assignment. If you have a problem with the limits, make sure you come talk to me, get that straightened out. So the left-hand side, I'll write it out in the long, explicit way. That's technically how you would put in the limits, right? Put in the upper limit and then minus put in the lower limit. But remember I said mathematically that's kind of nonsensical. It's kind of nonsensical because my speed has units and I can't have the natural log of something with units. So how do we rearrange this to make it mathematically more sensical?
Natural log of Bf over Vi.
We combine them. If you have natural log of A minus natural log of B, that's the same as natural log of A over B. Okay, you want to solve it for V final, so how do I get rid of that natural log? Use the inverse function of natural log, which is E. So I will have, once again, writing an annoying explicit. I'm going to drop the F. And so finally, the speed at any time is equal to the initial speed, e to the minus b over mt. Something to note here, that logarithmic or exponential, decay, that's a result of the rate being proportional to the rate of change is proportional to the value. In this case, it was the rate of change in speed is proportional to the value of the speed. When you have a rate that's dependent on the value, that's where you get this exponential function. So it occurs a lot in nature. Cody.
Take two differential equations, can we solve it that way, or do we have to do it through this way?
There, you have shortcuts in differential equations,
Yes, it's a lot shorter.
but this is, you should do it this way. Let's just leave it at that. It's true. We teach shortcuts like, well, look at the powers, and we're not going to have anything that a shortcut really helps with.
I do this in pretty much one step.
Probably because you say, well, I know that my answer has the form of this, right?
I mean, when you have B equals KD, BDT, it's going to be in that form.
Yeah. But yeah, do it explicitly. Humor me. Oh, that was the speed as a function of time. There was one other part. Find the position as a function of time. Well, how would I find the position as a function of time?
Separate variables and then take
Okay. I need to replace v is equal to dx dt, and then separate, which in this case is going to be the trivial, just multiply both sides by dt, and then integrate, and I will have my equation for position as a function of time. What if I want the acceleration as a function of time? Take the derivative with respect to time. Right, so the real work was done here. Question?
When we integrate vi e to the minus bmt, vi is a constant, correct?
Yes.
Okay, so we can treat it as a constant.
Yes.
Okay.
All right, the same problem, but at higher speed. One that's actually applicable to a bullet. If you're shooting a bullet, it's going really fast, and the viscous drag force actually goes to a higher power. And so we say, well, it's more like the viscous force is dependent on v squared instead of on v. Now, I'm not going to go redraw the free body diagram and do all of that. Instead, I'm just going to go straight to minus bv squared is equal to ma. Right, that's what this model gives us. Both of them are correct models. It just depends on the speed, which one is the correct model. So, following what we did before, what should we do? And then we have to separate variables and integrate. So I'm going to multiply everything by dt, divide everything by mv squared. Divide by the m because I want the v by itself. Divide by the v squared because, well, I've got to move it from one side to the other. And I'm left with the right side's the same, the left side different. Integrate both sides. What do I get when I integrate dv over v squared?
Negative.
I'm with you.
-1 times v to the -1.
Okay, we have v to the minus 2. We integrate, so we raise the power by 1, so it's v to the minus 1. And then we divide by that new power, so divide by minus 1. So it's exactly what Jonathan said. It's going to be minus 1 over v. And I didn't put the t initial here because it's 0. Well, in this case, and of course I didn't give myself enough space, but there's only like 2 more lines, so I'm going to go up. I'm going to have minus 1 over V final plus 1 over V initial equals minus B over M T final. Well, this is just going to take a little more work to solve. So, let's rearrange that to and then I'll drop the finals, don't need those anymore. And then you just invert both sides. Did you have a question?
How did you move VI over?
What I did was I added 1 over V final to both sides and added B over MT final to both sides. So the 1 over V initial is the only thing that stayed in the same place. Aaron.
For the speed or the position function for the last problem we just did, you have a natural log on one side and E on the other side. How do you simplify?
No, it's not going to be a natural log on one side. Okay. I didn't put in see why I wanted to put in full 8.5 by 11s? I was wondering why I didn't have more space, and it's not 8.5 by 11. Okay, so with this here, if I were to integrate, I would have dx is equal to V initial e to the minus B over M dt. That's using V equals dx dt and doing a roll one step short. The integrals with the limits.
Oh, that's a constant. It's not.
Yeah, the V initials is a constant. And so on the left-hand side, of x final minus x initial. And on the right-hand side, I have V initial e to the minus B over M t final minus V initial e to the 0. So the second one's just minus V initial. All right, so here I have my equation that if I solve it for V, I'll have V is equal to they're so not spaced there. I'm just going to end up invert this side, so I'll have V, and I'll put here raised to the minus 1 to show that that's inverted. That's about the easiest way to write it. So there I found the speed as a function of time. And notice I didn't ask you to go any further just because it would be a little more difficult to find the position as a function of time with this function. Okay, that's the end of my prepared review. We have 7 minutes left in class time for you to ask any old questions you have about the upcoming exam, or the other option is to walk out the door. So if you have questions, fire away. Out loud. As you can see, I chose 8.5 by 11. Better be 8.5 by 11. Can't tell until you write something on it, but I don't think it is actually. Yeah.
For the exam, I know you asked us to bring the protractor.
Well, if you have one.
Okay, yeah.
If you don't have one, we have, granted, they're missing from both of these. One of them's in my office, one of them got redistributed somewhere. Like right here, this one has 2, see? So we have these here that we will share when you need one, raise your hand.
What will we need to perform this test?
Because you're going to be adding vectors graphically.
Oh, okay. My question is, would we have to, would you have angles that we have to measure?
Yeah.
How precise do you need to be on this?
It needs to be careful. I'm going to use a ruler when I'm grading it and a protractor to make sure your angles and lengths are scaled right.
But maybe not quite to like the degree of precision you have.
Well, as an example, for the test that I'm giving the people over at Southwestern in their eating lab, I have to have a different one because it's a different time. In my solution that I did just before coming to class for theirs, I got from my graphical solution 6.6, and the answer was supposed to be 6.8. Well, that's close enough. Right, but if you're like 6 is close enough to 7, no, that's not. Don't tell them their answer is supposed to be 6.8, okay? Carrie.
For like figures for other puzzles where we're doing answer, we still need to measure it.
No, it just needs to be qualitative. Other questions?
You're okay with stick figures, right?
I am absolutely okay with stick figures. You see my artistic skill.
For vector addition, do we actually need to show adding the components, or can we do like log cosines? Like, are they both equally valid for each problem?
If I say to do it graphically, you better do it graphically. If I don't, you just have to do it a valid way. Yes. There is one problem that requires you to do it graphically. And so it will say on the one problem, this one has to be done graphically. Other queries?
When writing down the concept, so you just in the problem is that you wrote down like, here's how you do it with just variables before.
This is the A and this is the B, and then you take B and B, put it down here.
Yeah, I mean, if it says, find the speed given this position, you say the speed is the derivative of the position. That's all you need. Right. Just something that I know that you actually know what you're doing, that it wasn't random. Yeah. Let's put some numbers down and see if any of them are right.
For the, will we have an equations portion of that question?